Okay, in this video we're going to attempt to go through a problem set that's kind of uh, looking at problems that are designed from chapters 8, 9, and 10. Mostly I'm trying to integrate chapter 10 with chapters 8 through 9 so that you'll see this problem set here also as a useful exercise as you prepare for exam 4. So here's the problems, and you should be able to find a blank problem set that hasn't been filled out on the flipped classroom activities page for this class. All right, so here's our first problem. We're going to just write a mechanism for this reaction right here. Okay, and let me go to the drawing tool here. And okay, so let's center this problem here, and let's write a mechanism. Okay, this is a classic 1,2 versus 1,4 addition problem for a conjugated diene. All right, so first we're going to protonate our alkene, like so. This is going to give us a carbocation, of course. Okay. Let me just draw that other one as a CH2. All right, so what we have here is, of course, the allylic carbocation, and like all allylic carbocations, we have a resonance structure that we can write. Okay. And that's our other resonance structure right there. Some people will like the one on the left better because it has the tertiary allylic carbocation. Others will like the one on the right better because it has the more substituted alkene. This one is probably, the one on the left is probably the better resonance form because the carbocation is the more reactive species, and thus it's more important to stabilize that. Okay, so if we want to look at how we form these two products, okay, that we released chloride in that first step, right, when we protonated that. So we're just going to add the chloride there, and that's going to give us this product, and we'll add the chloride ion here, and that gives us this product. As far as which is kinetic, which is thermodynamic, you'd probably say that this is the thermodynamic product. Okay, and that's because this one is more stable. And this other one here is probably the kinetic product because it arises from the more stable resonance form, or the more important resonance form. It arises from the one where there's more positive charge. Okay, all right, but remember, in this course we don't really want to focus on what's going to be major or whatever. We should be able to predict the thermodynamic product by looking at the structure and figuring out which one is more stable. But the kinetic product requires some rather deeper considerations. Okay, let's look at this mechanism here. This is a classic SN1 reaction that has a carbocation rearrangement component. So let's look at what we're doing here. We're also going to make a byproduct here. Let me just paratoluene sulfonic acid. So that might become as important, but all right. So in the this is an SN1 reaction. Notice that this looks like a solvolysis. The halide, or the tosylate in this case, is secondary. Methanol is a relatively poor nucleophile, so it's not going to engage in any sort of SN2 or E2 behavior. Okay, so if we think about what's going on here, like in any SN1 reaction, the first thing we do is we make the carbocation. by just ejecting the tosylate group. And that gives us this carbocation. Notice that the ring sizes have changed, so there's obviously a 1,2 alkyl shift going on here. Okay, and so what we're doing here is we're just moving that group, this CC bond, right here where the arrow is starting, is doing a 1,2 alkyl shift. This is going to change the ring size from 6,4 to 5,5. Okay, our hydrogen is here. If we're going to, let's just put an asterisk there. Hard to make an asterisk with a stylus, but there it is. Okay, here's our carbocation now. Okay, we can see why this alkyl shift would want to happen, right? There's a lot of good things are happening here. We're reducing the angle strain. We're increasing the carbocation stability, where we're going from just plain old secondary to a carbocation that's now tertiary and allylic. Okay, so this is a very good carbocation. Since it's allylic, of course, it has a resonance form we can write. Okay, maybe running out of room here to write all these things, but you can more or less see that after the rearrangement has occurred, methanol can come in. Let's see. I'm just going to not draw the rest of that there because I'm running out of room to write. Okay. All right, so that gives us this, and we're going to lose the extra H plus to generate the final product. Okay, here, same thing is going to happen. Methanol is going to come in. Okay, again, I'm going to just give an abbreviated structure right here. Giving us this compound here. That's just methanol adding to the carbocation, and then again we're going to lose the extra H plus to make that. Okay, so this starts out as a classic SN1 reaction, but then after the carbocation rearrangements occurs, it does make an allylic carbocation. Okay, so these are all like a series of 3 or 2 to 4 step problems here. We're going to predict the product of each reaction. All right, so let's look at this one first, and this one. Of course, in step 1, we're going to turn the alcohol into a leaving group, which is a good thing because you can see that the next reaction is a reaction with a nucleophile. Okay, so we're at CH, triple bond CH. This tosylate is primary and should react by the SN2, regardless of the fact that this is a very basic anion. Since it's reacting with a primary substrate, we're not going to worry about the E2 happening. Sorry, this is isobutyl, not isopropyl. Okay, and step 3. It's alkyne hydration. Okay, sorry, that was not a good place for me to write this. Let's see, I need an eraser here. Okay. All right. Okay, let's go back to now drawing. All right, step 3. It's going to give me my isobutyl ether and 3 carbons, and then ketone right here with a methyl group. Methyl group there, and that should be our final product. Okay, and this one, NBS in light, is going to give us initially this radical right here. Remember, it's resonance stabilized. So in step 1, we're going to get a mixture of 2 bromides. Compound with the bromine there, plus a compound where the bromine is primary. This is primary, this is tertiary, also allylic, but we won't worry about that for now. Okay, so this is a strong base. So when this does the E2, when it reacts with the tertiary halide, it's going to do the E2. And it's going to make this. Okay, and this is a primary halide, so when it reacts with NaO2, it's going to do the SN2. And this is going to make the compound where the bromine is merely replaced by the OET group, right? So it's going to make the ether. So the primary one's going to do the SN2, and the secondary one, the tertiary one is going to do the E2. Okay, this one we're reacting it first with sodium ethoxide. And let's say that there's going to be 1 mole of each of this, and then we're going to react it with 1 mole of NaSET. So the more reactive one's going to get the OET group, the less reactive one's going to get the bromide. So this is primary and allylic, and this is primary. So this should be the more reactive site here. Okay, so in step 1, we're very careful to add exactly 1 mole. We should get the OET there. And in step 2, the remaining bromide is going to react with the other nucleophile that we add second. And this should be the product. Okay, so the OET reacting with a more reactive halide, the SET reacting with the less reactive halide. Okay, I think we finally have this one. So this one, we have a selenium and a sulfur. The selenium's further down in the periodic table and should be more nucleophilic. So in reaction 1, okay, we should methyl on selenium. Sulfur's the next reactive compound, so it's going to get the alkynyl group. In step 2. In step 3, we're going to take the terminal alkyne here. Remember, we have a hydrogen, and we're going to remove that proton and replace it with an ethyl group through the SN2 reaction. And so in step 3, we're going to get this compound here. All right, in step 4, we're going to do the Lindlar reduction, which is going to give us, turn the alkyne into the cis-alkene. So we should have something like this as our product. Okay, sulfur here, benzene ring. And that should produce that product right there. Okay, so first we alkylate the more nucleophilic species with the methyl group, then the remaining nucleophile, the sulfur, reacts with the called the propargyl bromide, or the one with the alkyne there. We're going to take the terminal alkyne and replace it with a methyl group by deprotonating and then doing an SN2 reaction, and then we're going to do the Lindlar cis partial hydrogenation. Okay, so let's look at this roadmap problem here. We have an initial NBS reaction producing probably an allylic halide, and let's see what we can figure out about this, which one is which. Okay, so you can probably figure out that the two products here are different, and they're due to the allylic resonance. So let's just remember that the radical that we're going to make more than likely is the one that's tertiary, like that. So we're going to have this, so our bromide will come from these two resonance structures. Now if you look at the rest of this problem, let's see, sorry. You can sort of see that C is going to require that we do some eliminations. So let's let's make A the one that's more likely to do an E2. That'll be the tertiary one. Tertiary allylic here. And B, we're going to make the one that's more likely to do an SN2 reaction, as you can see there. Okay, so these are A and B. All right, so if we treat A with this strong base, kind of hindered too. Okay, we're going to do the E2, right? Okay, and this gives us C, and it looks like we're doing a thermal reaction here, the Diels-Alder reaction. Okay, so in the next step, we're going to turn C into the Diels-Alder addict. Okay, and this looks like the right thing to do. Okay, this is a symmetrical compound, and remember that the stereochemistry is retained because it's a syn addition. So So the iodide and nitrile should be trans, and then this last step we're doing a CO2, SN2 rather, which goes with inversion, and that produces the final product. Okay, so let's look up here. Up here we now have the primary halide. We're also, in this case, hydrogenating it, and this is going to, in theory, make this compound right here. Okay, this is now, okay, I think I left a methyl group out of the product. Yeah, sorry, the product should have an extra methyl. I'll fix that on the answer key. Okay, this is now going to do the alkynyl anion addition to make the compound here, and the last step is just an alkyne hydration, and since this is a terminal alkyne, it's going to be regioselective, making the Markovnikov product. Okay, let's look at the last problem here. This is an organic synthesis problem, and let's see if we can find some elements, okay? All right, so if you look at the structure here, sorry, I don't know what this O is for here. Okay, all right. There's only one reaction we've ever known that makes, or we've ever had that would make a 1,1 dihalide, right? And that is to take a terminal alkyne and treat it with 2 moles of HCl. Okay, so that reaction is going to come into play. You can see that we have an epoxide. We also have this direction to use propyne, the anion derived from propyne, which is this species, as our source of extra carbons. Okay, but we see that we have an epoxide. Epoxide comes from an alkene, so let's think of this as where our extra carbons are, okay? Okay, so let's look at how we might want to go about making this compound. All right, so the extra carbons are going to come in later. We don't want to add them right away because then we would have a compound that has 2 alkyne groups, and that wouldn't be good. So we want to make sure that at all points in the synthesis we only have 1 alkyne group. So let's go ahead and do this reaction that's going to make the halide, the dihalide first. It's actually going to make a trihalide. All right, so this will make this compound right there. Okay, 2 chlorines at the same carbon. All right, now we can do our SN2 reaction by reacting it with the anion derived from propyne. It's probably the sodium salt, but we'll just draw it as the free anion. Okay, so that should make that. Recognize that if we look at the epoxide, it looks like it's coming from epoxidizing the cis alkene. So we're going to treat it with Lindlar's catalyst. This should make this compound now. All right, our alkyne be cis, and then add the peroxy acid, and that would give us the final product. Okay? All right, so again, considerations are we don't want to add the alkyne too early because we'd have a compound with two alkynes and that would create selectivity issues with our HCl. So we're doing this reaction with 2 moles of HCl first. Then we're adding the alkyne. We need the cis-alkene to make the epoxide of the right stereochemistry, so we treat the alkyne with hydrogen and Lindlar's catalyst, and then we treat the final product with peroxy acid to make the epoxide. Okay, all right, so that's the end of this video, and I'll also have an answer key on Canvas for you and the raw problem set as well.